Welcome back to ECE 442-542. Hopefully you are finding these videos. If you are not, what I'm saying won't matter, but I've been sending emails. Somebody said they couldn't find the video or videos, and those are now linkable through the content page on D2L. Hopefully you can find those, and you're hearing me now. Some other announcements is that tomorrow I won't be in office hours. I think at this early date in the semester that's not going to be an issue. But typically I will be in office hours on Tuesdays and Thursday mornings and Monday and Wednesday afternoons. And the times Monday and Wednesday are 4 to 5. Tuesday and Thursday it's 10 a.m. until 11 a.m. One thing that is due before we meet again is your passport. Only about a third of the class have submitted their passport, and there's really two stages or two different ways of completing your passport. One is the actual document that I want you to produce as a PDF and upload that into the assignments folder. The other is once you have your answers for step 3 and 4 on the passport, go ahead and take the quiz in D2L. You'll click on the quizzes menu item up above on the D2L website for this class, and you should be able to find a passport quiz, and that's simply filling in a blank and indicating a choice with a bubble on which particular chapter spoke to you by looking at Make It Stick. Yes. Pardon? If you submitted it using a Word document, that's fine. So typically it's easier for compatibility reasons. If you submit everything as a PDF, then I can load it. Sometimes the Word documents, the formatting, it gets all messed up sometimes. But hopefully a Word document is fine. If it isn't, I'll communicate with you and say, hey, I couldn't read your file. Can you simply convert it to a PDF? Homework number 1 is due then on the 3rd of February, which is a few days from now. But we are going to be talking about material that will be part of homework number 1. And you'll submit that similarly into an assignment folder labeled for homework number 1, and you can be reading a couple of different chapter 1s, and maybe next time I will tell you what specific sections in DTSF we are looking at when we're talking about solutions to first order or second order difference equations. And just so that it's on your calendar, exam 1 is scheduled for Wednesday, the 19th of February. Wow, that's even after Valentine's Day. So you have a little bit of time, about a month, before exam number 1. But we will have 3 exams in here. But I'm trying to actually schedule the exams a little later versus where you cover the content. A year ago, some of the online students were saying, wait a minute, we just covered the content and it was due, and now I have to turn right around and take the exam. I'm hoping now I'm giving you some time between when we have covered the material and you've submitted your work and when the exam is scheduled. So we'll be getting into new material prior to exam number 1, but I think you're now far enough along in your educational process to understand how that works or why that might be happening. We'll start today by reviewing or giving you some show and tell. I've brought in some show and tell. What I did over the summer, no. But I took a picture of the back wall of a conference room in the ECE building that actually has an analog simulator. I'll show you that if you were wondering what I was talking about when I was saying, oh, here's an analog computer. And an analog computer is really an interconnection of integrator blocks, summing junctions, and gains. And I just want to remind you how you can create or build an integrator out of an op-amp circuit. And now when I tell you, oh, here is a third order circuit or a third order system. It doesn't have to be a circuit. It could be a mechanical system. Now you could say, oh, that's an all integrator block diagram. Oh, I could actually build that in a circuits lab out of op amps, gains, and summing junctions and simulate that with an analog simulator if I wanted to. And today we'll talk about how we now might create a state space representation to allow us to do it in MATLAB, to simulate these systems in MATLAB. If we had unlimited time, I would, after I give you the show and tell, I would give you the challenge. I would say develop a state space representation for the second order circuit that we talked about last time. And you would then be frantically trying to figure out how to do that. And if you're online, I would pause the video and try to do that. The idea is coming from the Make It Stick material that you've looked at in terms of trying to generate a solution maybe before you've even been exposed to a strategy, a solution strategy. Then when we start talking about how to do it, you go, oh, that's what I wasn't getting, or that's what I didn't quite understand. And usually the connection is stronger than me just getting up here and walking through a solution or a strategy, and then you go, eh. So the challenge to the main campus students is to go home and before you look at the notes, try to rederive what we talked about today in class. Even pull out a circuit. Pull out a circuit. That means just create one on your own and see if you can create a state space representation for that circuit. And I'm emphasizing A because state space representations are not unique. I could generate a state space representation. You guys could generate 50 different state space representations, and they could all be modeling the same system just with a different representation that is equivalent. It would give the same results as what mine would or your neighbors might. We'll go through that. We'll go through the process actually of, and that's what I'm saying, we're going to review, continue, complete what we started last time with our electric circuit. How do we, starting with the differential equations that are coupled, how do we put that into a state space representation? We looked at an all integrator block diagram. Then we'll go from there and we'll start doing discrete time analysis with difference equations. And we'll look at a couple of those. A homogeneous, that's a bank account where homogeneous is meaning we just make a deposit and we watch our capital grow. We aren't putting in any deposits. Then we'll talk about a non-homogeneous, which is now we'll just sort of flip that and say now we are going to be putting an input in, but now this is on a loan repayment. So the input is actually what we are paying and trying to pay off this loan. But again, it's a difference equation, linear difference equation. And then we'll go into more general ideas of homogeneous and non-homogeneous difference equations and their solutions. We're talking now digital control, which means that we do need to understand how to model and analyze difference equations. Here's the picture in the back of the conference room. It's an analog simulator, and this was actually created with some faculty members here a few years ago, quite a few years ago, with Burr Brown. Burr Brown was a company here in town created by some entrepreneurs many years ago. They were bought out by Texas Instruments, but Burr Brown created, with the help of some faculty members, this analog simulator. And maybe you can see on that panel some integrators. You now interconnect your integrators, gain blocks, summing junctions on that. That's how you program your analog computer. Then you inject a waveform into that and out pops, or you can now measure the output response. And instead of now having to build a physical system before you understand how it might behave dynamically, now you could wire it up, you could program it in the analog computer and run the simulation or perform the simulation. What's behind those integrators? Here's an integrator created from an op-amp circuit. We just interconnect a capacitor and a resistor. The capacitor is providing the feedback path from the output to the inverting node of the op-amp, and you inject an input at the input terminal V sub I, and out comes the integral of that signal or that waveform as V sub 0 of t. And you can convince yourself of that with the following analysis. I'm going to kind of scroll through this. I gave this to you in the template form, and we want to get a little bit further than this, so I'm just sort of quickly going through this as a movie. So I'm not necessarily going to allow you to keep up, maybe, but if you're quick, you can. But now you could write KCL at node A for this op-amp circuit. All of the currents going into that, or you could say, oh, here I've indicated two currents going in to that node and one going out and one going into the inverting terminal of that op-amp. That, by the ideal op-amp assumptions, or the way op-amps are built, doesn't allow current to go in to that terminal. So essentially we are summing the currents into that node A, and the fact that we have negative feedback allows us to assume that the inverting and non-inverting voltages are approximately the same, so that node A is essentially at ground, is a virtual ground. That allows us then to say the current going in from V sub I is V sub I over Z sub I. The current going in through the feedback impedance is VO over Z sub F. And now we just solved that for VO over VI. We're not going to worry so much about the negative or the inversion of the signal. But now if we used the passive elements in the appropriate locations for the input impedance and the feedback impedance, Z sub I was just a resistor. The feedback resistor was a the feedback impedance was a capacitor. It's 1 over SC. We now plug those in and we obtain minus 1 over S RC. We know multiplication by S in the frequency domain is differentiation in the time domain. 1 over S in the frequency domain is like integration. You can now say, oh, here's our integrator, our integration operation built from an electrical circuit. And in the time domain, if we inverse Laplace transformed, we would see, oh, the output waveform is just a weighted integral of the input by the construction of that op-amp circuit. Now's when you can pause if you're at home playing along. Now recall what we talked about last time, which was this second order RC circuit. Can you now derive a state space representation for that circuit? Here's the circuit, or from the previous lecture, and we were analyzing it in the time domain. We were using Eli and ICE. We didn't have to worry about Eli. We had no inductors here, but we did use ICE to give us the voltage current time domain relationship, or current voltage relationship associated with capacitors, to allow us to write node voltage analysis, and we get red and blue equations. Node 1 is blue, node 2 is red, and now we have coupled first order differential equations. This we did last time. Those equations should seem familiar based on what we talked about last time. Now what we want to do is put that into a state space representation. And I've actually already subscripted the variables to help us with that. We want to now stack these state variables into a vector on top of each other, and in this case we just have two components in that state vector, an x sub 1 component and an x sub 2 component. And our state space representation, well, I'm getting ahead of myself. I'm talking before I'm looking at the movie. But suppose we plug in some numerical values for r's and c's. Then those coefficients collapse down to some numerical values, and we have x1 prime as minus 3x1 plus x sub 2 plus 2u. And the time rate of change of the second capacitor voltage, x sub 2, is now a linear combination of the voltage across the first one and across the second as 2x1 minus 2x sub 2. Now what we want to do is put that into a state space representation, which is stack the x1 and x2 on top of each other. We want to find an x1 prime over an x2 prime equals some matrix times the vector x1, x2 plus some matrix times the input. And now I'm hoping with your 310 expertise, maybe I should say that's a prerequisite for this class, but you kind of have that before 320, yes, no, or at the same time. Or if you've had some linear algebra, or even if you have not, hopefully you know matrix multiplication. And now looking at the top, or those two equations above the blue boxes, can we fill in the matrix elements? What's in the 1, 1 entry, and I'm going to actually refer to this matrix as the A matrix. And that's going to, in fact, be what I will call the system matrix. That matrix, to be compatible with the left-hand side of the equality sign and what it's being multiplied by, it has to give me two rows to be consistent with the left-hand side of the equal sign, and I'm now ending up with a two-row matrix that multiplies by a vector that has two rows. How many columns are in that matrix? 2. This system matrix is always square, and in this case it's 2 by 2 in this system. I now have 4 elements in this matrix that I should be able to find or identify from the two coupled differential equations. What's in the 1, 1 entry? Minus 3. And the 1, 2 entry? The 2, 1 entry. And now, by a process of elimination, this is minus 2. What are the dimensions of this? Is now our input matrix, which generically I might just label as B. What are its dimensions? 2 by 1. I'm only assuming I have one input in this case, one voltage U. Now I'm looking at, it has to be compatible with the left-hand side. And these ideas for continuous time, matrix stuff, follow through into discrete time. So understanding it now is going to be beneficial when we talk about difference equations and finding the state space representation in the difference equation or in the discrete time setting. It's just that we will now be doing differences instead of derivatives, or we will have shifts in time in the difference equation. What's the 1, 1 entry in the B matrix? 2, and the 2-1 entry. What did I say? Yeah, I guess I said the right thing. I get in front of the camera and I sometimes don't remember what I've said. I need my teleprompter, which is where? Where is it? Now we also have an output equation, which is a linear equation. There are no dynamics in this set of equations. We simply arbitrarily picked the X sub 2, or the voltage on the second capacitor, to be our output voltage. This is now our output matrix, which I might label as C. And this is now the direct feed-through matrix. Which simply means that is a direct connection from the input to the output. Is there a direct connection present? And in our case, y was simply x sub 2. We simply need to pull off x sub 2, and that's it from this structure. Now we have our state space representation for that circuit, second order circuit, and we could just put all of those now together. I was thinking I wouldn't necessarily identify the A, B, and C before, so I put it in where it now is living. Now what I failed to do in doing this ahead of time is, I'm sorry, you're going to maybe need some scissors or maybe just an extra piece of paper. I'm actually going to put one more idea in, and that is to think of this state space representation as a block diagram in a general form without having all the integrators explicitly identified. Meaning, I want to now put together a block diagram of this state space representation in the form of just A, B, C, and D, and not explicitly showing all of the interconnections. Or I now am trying to say, here is a bank of integrators. If it was a sixth order system, I would now have 6 integrators. And going into that integrator bank is now the derivative of my state vector. Which means the output is going to be each of my state variable components, x. And how do I build x prime? X prime is now equal to ax plus bu. Or I now have ax. I know where x is. That's right there. I can now scale or multiply it by a and feed that in to give me part of x prime. The other part of x prime is from the input, which comes in through appropriate directions determined by the input matrix B. There's u of t. Or now there is my coupled set of first order differential equations in a block diagram, and that gives you now a different way, a visual way of thinking about differential equations. Now they are interconnected by some collection of integrators. This is now a bank In our particular example, that would just be a bank of 2 integrators. And now we want to finish this by building up the output. Or we can do that by doing, we need a C times X, and it's possible that we might have a direct feed through from the input, and now this is maybe poor choice of colors. Let me change that so that you know that that goes there, and this is now coming in there. That now provides you with another way of thinking of these first order differential equations in a block diagram structure. If you wanted to, you could now expand this, do an exploded view of this, and say, I want to know exactly how all of these different integrators are interconnected with my various elements in my A matrix and B matrix, C matrix, etc., which is what we built last time. What we want to do now, though, is take this state space representation and take it into the frequency domain. We want to now Laplace transform this system of equations, which means then that we have to remember, really, the only sort of interesting part of this process is remembering what happens when we Laplace transform a derivative. And in fact, I'm telling you that, but we're after the fact going to say, well, if we're interested in transfer functions, we can neglect the initial conditions, but when you Laplace transform a derivative, what actually happens? If I now said, Laplace transform x, well, maybe let me change that because x now is going to be a vector. So let me just say we have a variable v prime of t. What happens when we Laplace transform a variable, just a single variable, v prime? What's its Laplace transform? Multiplication by s. Do we have anything else? We have to account for the initial condition, which is now minus v of 0 minus. That's how we Laplace transform a derivative. What we want to do now is Laplace transform a vector of derivatives. That's what x prime represents. That's now a stacked column of derivatives of different variables. x1's derivative, x2's derivative, x3's derivative. What would you speculate that looks like? If this is now the Laplace transform of a variable, what happens when we Laplace transform a vector of derivatives? They all get multiplied by s. This complex frequency variable s can now just apply to every one of those. So now capital X is a column of all of these little x's that have now been capitalized. We've taken them into the frequency domain. We now have capital X sub 1 of s on top of capital X sub 2 of s, etc. And if we keep that full-blown theory in place as far as what happens when we Laplace transform a derivative, we need to then account for the initial condition. But since we're interested in the transfer function, we're going to be able to neglect that piece. But it's in the process really there. We're just going to be able to neglect it when we're trying to find the transfer function between the input u and the output y. What happens now when we Laplace transform the matrix A times the vector x? What is the matrix A? Does it have any time dependence in it? No. That's a constant, so the Laplace operation slides right through that matrix. All we have to do now is Laplace transform the vector, and in this case, that really just represents a capitalization of that time domain set of variables. Or now we have this is equal to A times capital X of S plus, and the same holds true for B u of t. B is not a function of any time. It's constant. We now have B times u of s. Now we want to solve this for capital X of s in terms of u of s. That's going to be a little bit of a challenge without making a connection. Right now, s is a single complex variable, and that's weighting all of the components in this vector capital X of s. But we want to somehow factor out capital X of s, and on the right-hand side, it's multiplied by a matrix, capital A. So now what we want to do is actually make this compatible so that we can factor out x, and the way to do it is to simply introduce the matrix identity, and that now collapses effectively when we say s times capital I times capital X of s, but it gives us the placeholder that we need when we want to now combine s x of s with a x of s. Meaning, we can now say, oh, this is now si minus a times capital X of s equaling b u of s. Now we can invert that parameterized matrix. It's parameterized in a parameter of the frequency variable s. We can now invert that to solve for the Laplace transform of our state vector if somebody now gave us the Laplace transform of the input, which in this case is a voltage, we could then compute si minus a inverse times b and obtain how that is now filtered to produce the Laplace transform of the first capacitor voltage and the Laplace transform of the second capacitor voltage, which are stacked on top of each other in this capital X of s vector. We want to actually find the transfer function between the input u and the output y. We can do that by going back up here and Laplace transforming the output equation. And that's now no derivatives. It's a linear equation. We can now simply capitalize all the variables and find that we now can state that as y of s is equal to c x of s plus d u of s. This is the Laplace transform of the output equation. And if we replace the right-hand side of capital X of s and substitute that away, we will now have an equation that only contains the output's Laplace transform, which is capital Y of S, and the input U of S. Or we now have Y of S is equal to C times SI minus A inverse B. That's times U of S plus D U of S. We can factor out the common input's Laplace transform. And that mess here is now the transfer function that we were after. If somebody now gave us a state space representation, which means they gave us an A matrix, a B matrix, a C matrix, and a D matrix, you could now find the transfer function between the input U and the output Y by using this formula. It's now the matrix C times this symbolic matrix SI minus A inverse times B plus D. In our case, D was not there, so it collapses away. But this now is a way to go from a state space representation into a transfer function. And we've now gone from the time domain into the frequency domain. Where the transfer function is really, we're assuming now a single input, single output case is the ratio of the Laplace transform of the output over the Laplace transform of the input. Let's just go through that so that you can practice your linear algebra skills. We had the C matrix, that was 0, 1. We had the A matrix. We now take SI minus A, and that gives us this S plus 3 minus 1 for the top row and minus 2S plus 2 for the bottom row. We invert that, which means we take 1 over the determinant. The determinant of that matrix is S plus 3 times S plus 2 minus the off diagonals product, which is 2. That's what you see right there. That's the determinant of that 2 by 2 matrix. Then what happens? Then we actually just do the trick that only works for 2 by 2 matrices. Instead of worrying about the cofactor matrix transposed, we just say just flop the diagonals or switch the diagonal entries and negate the signs of the off diagonal entries. And that's now our inverted 2 by 2 matrix. We now pre-multiply that by the output matrix C, which is 0, 1. What's that do? If we now multiply 0, 1 times a 2 by 2 matrix, that effectively pulls off the second row of that 2 by 2 matrix. Then we're going to post multiply by a column that's 2, 0. That's only going to scale the first column of what it's multiplying by 2. You do all of that, and you end up with the transfer function that we're after. What I actually did is I performed this multiplication first, which means I take the first column in that 2 by 2 matrix and scale each entry by 2. And I weight the second column by 0 and add that in. So I'm throwing it away. Now I have a 1 by 2 times a 2 by 1 And the 1 by 2 is just saying pull off the bottom row in that 2 by 1, which is 2 times 2, or 4. And I end up with my transfer function, capital G of S, being 4 over the quantity S plus 1 times S plus 4. And based on your knowledge from 320 or something similar, if I ask you, is that particular system stable, what would you say? Is that system, capital G of S, stable? And there's several ways you could kind of come up with an answer for that. One is, well, he derived that from an RC circuit. And what does an RC circuit do? Does that go unstable when you excite it? No, that just dissipates the energy that you put into it. So you would expect it to be stable. Here, if you now say, oh, that denominator has roots of -1 and -4, those are in the left half plane, those are stable. Those have exponential decays associated with them. This is now, if you walked up and kicked that system, which in this case, walking up and kicking the circuit means you maybe energize the voltages on those capacitors and see what happens, they are just going to exponentially decay, the voltage on those capacitors. Because you now have modes, e to the minus t and e to the minus 4t, making up that system's dynamic behavior. What we want to do is become comfortable with the dynamic behavior of discrete time systems. For that reason, let's now look at some difference equation examples. And we'll start with a homogeneous. That just means we don't have an external forcing function or something driving the system. There's no input into the system. That's the homogeneous adjective. And linear means that we don't have products of terms or nonlinear expressions. We don't have a sine of x or a x squared in our equations. To illustrate this, let's just look at a system that I hope you're somewhat familiar with, a bank account. Suppose now you simply put down an initial deposit of $1,000 and you let your money grow. And let's not get too risky with this. Let's say that it's in a fairly secure investment and it's going to give us 2% annual growth. How do we start creating the behavior of this bank account by means of a difference equation? Or in this case, suppose that I now sort of give you a hint and say, suppose that we let this be our state of our account after 0 years. That's the subscript 0. So our initial balance is really our initial condition. This is now our time index, the sub-0, and this is the time after year 0. So that's our initial condition, x sub 0. We now want to relate that, x sub 0, to the balance after 1 year, x sub 1. And I've given you all the information that you really need. You've deposited $1,000 and you wait a year. What are you going to see at the end of 1 year? That's x sub 1. Well, I said it wasn't very risky, so you better get your initial balance, right, x sub 0, and then what you're letting somebody else have your money, so they're paying you interest on that to the tune of 2%. You're not setting the world ablaze, but this is now going to be 2% of what you gave them. Or we have x sub 0 in both terms on the right-hand side. We can now just combine those, and we now have a relationship between the initial balance and the balance 1 year into the future. Or at the end of 1 year, we have 1.02 times x sub 0. And you could start, if you wanted to, saying, well, I would like to sort of see this more visually. You could start drawing a time response picture to what's happening. At time 0, you had 1K. Then at the end of 1 year, now you have that plus 2% of that. So this is now, it was there, and now I'm showing much more than 2%, but you get the idea. There's now our balance after 1 year. Then what happens? What's x sub 2? Can do the same logic, the same process is happening. Or this is now 1.02 x1, but we know how x1 is related to x0. Or we now can say, oh, x2 is 1.02 squared times x sub 0. And now we know how to relate either x sub 2 to x1 or x sub 2 to x sub 0. And I hope you can see that what's happening here is I know you're not going to get too excited by it, but it's actually exponential growth. It's just not very big in terms of the exponential. But if you wait long enough, it will amount to something more than $1,000. So what happens in general? We could get this closed form expression, meaning I give you a year and you can immediately tell me what the balance is after that year. It's closed form. We didn't have to iterate to a solution. So this is now a closed form solution, or you could call it an analytical solution, or maybe an explicit solution. But we could also have just continued iterating and saying, well, if you tell me what you were at time n, in year n, I can tell you what your balance is going to be 1 year later by this linear difference equation. This is now a linear difference equation. If you had the time, you could now enumerate to a value if you wanted to, using that difference equation. Or you could maybe say iterate. So now you have two different ways of sort of thinking about this, but we will be playing mostly with these difference equations, but we will want to get comfortable with finding analytical solutions. Or given an initial condition, can you tell me what the value is going to be at some subsequent time period? It doesn't have to be years, it could be milliseconds. It depends on what our sample period is, without iterating to that value. For first order, it's fairly straightforward. But now what we may want to do is talk about this more in general, or in this case, what would have happened if you would have said, oh, you know what, I have money and every year I'll throw off 4% to you. Isn't that what they say you can maybe take out if you're talking about retirement? You now have this next nest egg. They may be, the sort of general rule was, oh, you can extract 4% and maybe you won't outlive your money. So what would happen if we did that? What would happen if we removed 4% each year? What would the difference equation look like? Do you know how to build it? What is x sub 1? We just take away 4% of what we started with, and we now have, and based on what we've looked at before, you can say, oh, this is now and what's going to happen to that balance? This is now an exponential response, but it's now an exponential decay. Similarly to how we've looked at e to the minus 6t or e to the minus 2t, that was an exponential decay. Now, what's the relationship between 0.96 and 1.02? 1.02 was exponential growth. 0.96 was exponential decay. What's the sweet spot between those? 1. If you didn't add or subtract anything, you would just be stuck, right? You would have x1 is equal to x0. x2 is equal to x1, which is equal to x0. You would be in a steady state. So now stability in the discrete time setting is all focused on that value 1. If we have a mode that's less than 1, I'm doing this. If you're listening, you need to now create a circle in front of you with your fingers, and that's now the unit circle. We want our modes, our poles, to be inside the unit circle. The unit circle has a radius of 1. If we have modes inside the unit circle, then we're going to have decay, stability, exponential decay. If our modes are outside, which is what you want on a bank account, you want your modes to be outside the unit circle, you want your balance to grow, now you'll have exponential growth, but in a dynamical system that may lead to an unstable, that will lead to an unstable response. But just sort of a point of reference. In general, if we're talking about now a homogeneous difference equation, we could maybe write that as x, and now we might, instead of subscripts, I might put the time index inside some arguments. We might say x at time n plus 1 is a function of x of n minus 1, all the way down to x of n minus k minus, you know what, I'm terrible with k's. Can I do L minus 1, and that's now my homogeneous difference equation. I don't have anything forcing that. I just have previous values of my state variable x. What's the order of that difference equation? And in this case, it's not necessarily linear. It's just a function. So the x's at different times could be multiplied together. They could be squares, square roots, sinusoids, whatever on the right-hand side. But if they were linear combinations of those, then you would have a linear difference equation. In this case, how many of these terms do we have inside the argument of f? How many previous state variables, previous so many terms in this sequence, or creating the next value of the state at time n plus 1. So now if you just kind of used your fingers and toes, you could sort of count that up for a given L. But you're really sort of starting at 0 and going up to L minus 1. So in fact, there's L terms in that argument for f. And because there are L previous terms, this now says that we have an Lth order homogeneous difference equation. And if you don't buy that, you might just do an example. Suppose we let L equal 3. Then x at n plus 1 is equal to f of x of n, x of n minus 1, x of n minus L minus 1. L was 3. So we now have x of n minus 2. And how many terms? We have 1, 2, 3 terms. This is now a blank order difference equation. Now instead of looking at powers of derivatives to determine what's the order of the system, when we're dealing with difference equations, we need to know how many previous indices do we have, or how many previous terms in this variable, state variable description of our next value do we have. In this case, we have 3, so this is now a third order difference equation. Let's look at another example. So that was the first one. Let's now look at a linear difference equation and maybe its solution. And as I hinted before, this example is going to be a student loan repayment. Probably none of you have to worry about this, but let's just be hypothetical. Student loan repayment. And maybe I'll be optimistic on this student that has the loan. Let's just say that the principal balance when they need to pay it off is $10,000. And if we're now going to use this, that would be our x sub 0, but just to be different, let's call it p sub 0. This is now our initial balance, just to get used to using different variables for state variables. Now we're using p. This is now our initial balance. And suppose that the interest, just to give us something to play with, suppose the interest now is 5%. And that's our annual interest. And suppose we want to pay this off with a time horizon of 10 years. We could, sort of on the back of an envelope, try to get a visual image of what's going off. We're going to try to pay at the end of each year some fixed amount to pay this balance off in 10 years. And we want to know what is that yearly payment that's going to be required to make that happen. We started with P sub 0 of 10K. What happens next? Would that just stay at 10K? Whoever is servicing this loan is charging us 5% interest. If we didn't do anything, that balance would increase by 5% after 1 year. Meaning we are now 5% above this dashed line. But what we want to do, so this is now P sub 0 times R. Boy, I can't write that small. Where R is, I'm using 0.05 interchangeably. That's now P sub 0 R, but what we want to do is in fact drive that down a little bit. We want to pay it off U so that after 1 year maybe we are at this location, P1. And we want that U to be the same for the next 10 years. Such that once we get over here to 10, we're now down to 0. This is now P sub 10 is equal to 0. And if this happened to be 2 years, we would be at P1, which would get bumped up P1R, but then taken away a little bit of U. So that hopefully with the U we're down below where we were at P sub 1. P sub 2 is now there. Or we can start writing the equations. P1 after 1 year is P sub 0 plus P sub 0 R minus U. That's what we did pictorially, and that's what we're doing analytically. Or this now becomes 1 plus R P sub 0 minus U. That's P1. What about the second year? I guess it's past my bedtime. That's P sub 1 plus P sub 1 R minus, or P sub 1 times R minus U. This is now 1 plus R P1 minus U. Or what's the general difference equation? Hopefully determined by that pattern. Could you now write down P sub n plus 1 is equal to something. And that's true for n equals 0, 1, all the way up to 9. When n is equal to 9, will it be at P sub 10, which we want it to be 0. We now have and is this nonlinear or linear? It's linear. We don't have any product terms or any funny nonlinear relationships on P sub n. That's our state variable. This is a linear difference equation. Can you now create a block diagram for that? And now this block diagram, since it's in discrete time, is an all delay, not an all integrator, but it's an all delay block diagram. Which, what we will do now, instead of having an integrator, we are going to have a unit delay. And in our particular example, that unit of time is 1 year. Which, if I now put as an input the balance at time n plus 1, and then I delayed that by 1 unit, what's going to come out of that unit delay? That's now P sub n. Right? So P sub n is a delay, 1 unit delay from P sub n plus 1. P sub n plus 1 could be P sub 2. We delay it. That's actually what we had at P sub 1. Now what we want to do is build up, or really just create that equation at the top of the screen through this block diagram. Hopefully you see that one term is going to be 1 plus r scaling P sub n. And that's coming in with a positive sign. And we have minus u. This now is an all delay block diagram for that linear difference equation. So if you didn't like looking at a difference equation, now you can look at it as a block diagram. And what happens? Well, that unit delay is like a storage container. You just put something in and then you wait 1 sample period and you pull it out. It's delaying by 1 unit of time. In this case, it's a year. What we want to do is we want to find what is u. We want to drive this system in such a way that it starts at 10,000, but we inject a u every year to try to drive P sub 10 to 0. Can we do that? So we know P sub 2 is 1 plus r P sub 1 minus u. But we could rewrite P sub 1 in terms of the original balance, P sub 0. That was 1 plus r P sub 0 minus u. And we can't forget the minus u. This was P sub 1. Are we okay with what I've done? Or we can now rewrite that as 1 plus r times 1 plus r P sub 0 minus 1 plus r u minus u, and maybe for bookkeeping purposes I'm going to write 1 as 1 plus r to the 0. Those formulas should be the same, or this is now P sub 2 is 1 plus r to the 2 p sub 0 minus 1 plus r u minus 1 plus r. What if I now wanted p sub 3? Do you know what that's going to look like? Do you see that I'm going to have these different powers of 1 plus r scaling u? And they're going to go up to 1 less in power than what I end up with that scales p sub 0. Or I now have 1 plus r cubed p sub 0 minus 1 plus r squared u minus 1 plus r 1 u minus 1 plus r 0 u. Or I could say now for a capital N, that's 1 plus r to the capital N minus some S-O-M-E of a S-U-M scaling u. And what is that? Well, now this is this summation from L equals 0. That's that of 1 plus r to the L, and then I go up to this, which is capital N minus 1. And in fact, if I could figure out what this is, then I could solve this, because I know capital N, if I set capital N to 10, I have everything I need other than the unknown u. P sub 10 is 0. P sub 0, whoops. I said it was past my bedtime. P sub 0, right? It's 1 plus r to the n times the initial balance, P sub 0, minus this mess of a sum times u. How do we find S? So now leave some space and say that S is equal to 1, which is 1 plus r to the 0, plus 1 plus r, plus 1 plus r squared, up to 1 plus r to the capital N minus 1. We okay there? Now, we're trying to find S. We know R, we know capital N. What if I now take 1 plus R and multiply it by S? What happens to the right-hand side? I now have 1 plus R times 1. So that really gives me this 1 plus R. I have this 1 plus R times a 1 plus r, or that gives me now 1 plus r squared. I keep doing that. But now I can widen my paper because I now have one more term. Because I multiplied 1 plus r raised to the power n minus 1 times 1 plus r. That gets rid of that minus 1 in the exponent. Do you see what I'm wanting to do now? I now want to compare these two expressions. By compare, I'm subtracting those. I now have s plus rs on the top row, and I want to subtract from that this bottom row. On the left-hand side, I have an s, and I take away a s. And am I left with anything on the left-hand side? Little r times s. I now have little r times s on the left-hand side. What do I have on the right-hand side of my equality? I have a minus 1 since I'm subtracting that second, and then all these other terms cancel except for that very last one, which that was what I was subtracting from. It now comes down without a sign change. Now I have a way of solving for S. We know little r, that was 0.05. We know capital N, that was 10. We can plug all of those numbers in and find S. You're going to run home tonight and figure out how much this is going to be, right? What is U? What will you have to pay? It's obviously going to be more than 1,000 because you had 10,000 and you only have 10 years to do it. So there's the answer in the back of the book, sort of. It's more than 1,000. We'll pick up somewhere close to that on Monday. Yes?
So what do you call S? Is there like a...
S is just going to be the sum of this fine. So what do I call S? S is just the sum of this sum, S-U-M. Finite sum.